Good afternoon. Representing the Santa Clara University Faculty and Staff Affordable Housing Development. I'm Aya Gufmi, in charge of the construction engineering for this project.
I'm Deirdre Vonitz, in charge of the potable water and wastewater on the project.
I'm Rachel Hahn, and I'm responsible for the environmental engineering part of this project.
And I'm Spencer Saito, and I focus on the structural engineering aspect of this project. Our presentation will begin by discussing how this project came about, then focus in on the main aspects of this project, and end with a few closing statements. Now I'm going to pass it off to Rachel to talk about the project need and background.
Thanks, Spencer. There are many reasons this housing development is needed, with the first one being that there are limited options for SCU faculty and staff for affordable housing. In 2018, only 60% of San Jose's affordable housing goal was actually constructed. This makes it difficult for faculty to find affordable places nearby and results in over 75% of faculty and staff commuting an hour a day. According to a survey conducted in 2019, where 930 faculty and staff were interviewed, the housing income burden they face averages around 33 to 34%, with a total income burden of 46%, including student loans and childcare. Fortunately, the rates that are being proposed for this development are 7% below the market rate within a 5-mile radius of SCU. Lastly, over a third of assistant professors interviewed are interested in renting from this development to save for future home ownership and shorten their commute drastically. Completing this project will help retain the faculty and staff that are key members of the Santa Clara community. Our team cares a lot about the faculty and staff at Santa Clara, as they have been critical to our college experience. So that is why our team has designed a mixed-use housing development for SCU faculty and staff in partnership with Facilities and Studio TSquare. 1200 Campbell is directly south of the University Villas. It will be a 7-story mixed-use building, with the first 2 floors being commercial space and parking, and the upper 5 floors housing the 290 residential units and 2 courtyards. Let's get into the considerations we've taken in our design. Aya will start us out.
Thank you, Rachel. Throughout the design, considerations for the economic impact of development were considered, as Santa Clara University is adding to the effort to provide affordable housing to teaching and staff professionals at Santa Clara County, and this development is a good step in that direction. Along those same lines, the impact of this building and its purpose speaks towards SCU's ability to help the less fortunate in the area, a clear Jesuit value.
The 2 main environmental considerations for this project are to 1, reduce construction waste, and 2, reduce the potential contamination of soil.
The main aspect of the health and safety consideration was to ensure that the building was designed to meet minimum code requirements and provide a factor of safety in the design.
The considerations for sustainability are to mitigate pollution from the decrease in transportation and to implement low-impact development on the site.
Socially, our design has adjusted to satisfy the demands of maintained privacy of residents who live in the adjacent Encanto community and the desire to find use in the commercial space on the 1st floor. Politically, we have been sensitive to the land being indigenous to the Ohlone and the Muwekma Ohlone people in our construction schedule, like requesting an archaeological dig and adding native plants. Now we're going to delve into the design components we were each responsible for during this project. Spencer will start out with the structural scope.
Thank you, Rachel. My original intent was to conduct a structural design from the bottom to the top, but due to constraints resulting from the university's transition to no face-to-face meetings and online classes, the project scope was modified to omit the following design items, such as a foundation, parking garage ramps and concrete slabs, connection details, non-load-bearing structural components, and steel concentric bridge frames. Based on the architectural drawings that were provided by the architects, Studio TSquare, Santa Clara University, and the stakeholders of this project, the entire skeleton of this building was determined to be 7 stories high. The key elements of this development consist of a parking garage on the first 2 floors, commercial space, which is only on the 1st floor, a clubhouse, which is only accessible on the 3rd floor but is 2 stories tall, residential units on the 2nd to the 7th floor, and a unique aspect of having an open courtyard beginning on the 3rd floor. Therefore, the layouts of the floor plans were designed for ease of construction and to meet the intended design parameters established by the client, Santa Clara University. The floor plan layout of the ground floor and level 2 were the same, and the floor plan layout for level 3 and above have a relatively similar layout to one another. A stairwell and an elevator are located near the 4 corners of the building to provide various options in the event of an emergency. An alternative analysis of 3 different construction materials, concrete, steel, and timber, was conducted. The design team created a list of criteria and a ranking system to justify which materials to use to design and build this new development for Santa Clara University. Timber is the typical material used to construct residential developments, but after applying this alternative analysis, steel was determined to be the best primary framing material, with the exception of using concrete for the parking garage. This decision was mainly due to the team's design expertise and the need to have long-spanning members throughout the building. The 2019 California Building Code and ASCE 716 were referenced to determine the dead and live loads for this building. For simplification of design, the columns were designed based on its location in the building, and the beams were designed based on its span length. The gravity system was designed using deflection limits per the 2019 CBC. In result, concrete and steel W-section columns and beams were designed. A pre-camber beam design was utilized for spans greater than or equal to 30 feet to reduce the sizes of members needed for the design, and the ASC catalog was used to spec the metal decking. Seismic design measures played a key role in this development since it is located in a high seismic zone. The equivalent lateral force method was utilized, and the ASCE 716, along with the 2019 CBC, were referenced to determine the design parameters such as the response modification factors and drift limit. A 2-stage design process was conducted, which led to the conclusion of designing the lower levels to be stiff and the upper levels to be flexible. Therefore, special steel concentric brace frames and special reinforced concrete shear walls were designed for the lower levels, and special steel moment frames were designed for the upper levels. There were 2 different lateral force resisting systems used for this structure, which ties into the unique aspect of how this building was designed. The first lateral system consisted of special reinforced concrete shear walls connected to special steel moment frames above. Presented are a couple of details that were created to help illustrate the design of this lateral system. The second lateral system consists of special steel concentric brace frames connected to special steel moment frames above. Presented are a couple of details that were created to help illustrate the design of this lateral system. These images shows a section view of the floor plans that compare the layout of the rigid versus flexible lateral system. Continuity and symmetry played a big factor in the design to ensure that the lateral loads were evenly distributed throughout the building and torsion did not occur. This outlines a process of how this project can be implemented for a future design project to especially focus on the scope of work that was omitted from this project. And now I'm going to pass it on to Deirdre, who will talk about the potable and wastewater management.
Thanks, Spencer. I'm now going to discuss the potable water and wastewater management systems that are on the project site. So here's an overview of this section of the project. For the potable water, we will be calculating the water demand using standard fixtures versus water efficient fixtures, sizing the mains and laterals, and locating the fire hydrants and laterals. For the wastewater, we will also be calculating the water demands and sizing and locating the mains. Finally, we will look into if using water efficient fixtures that reduce indoor water demand will reduce costs in the long run of the project and be as economically sustainable as it is environmentally. The water demand for the building was calculated taking into account the residential demand, the commercial demand, and the fire flow of 6,000 gallons per minute. This was done for a baseline demand which uses standard fixtures and a reduced demand that uses water efficient fixtures such as ultra low flow toilets and water sense shower heads. The potable water demands took into account the flow rates of the fixtures, the building occupancy, how many times people use the fixtures during the day, and the duration. In addition, peaking factors for peak hour and max day were also taken into account in the design. Presented as a summary of the calculations, as you can see, the baseline demand uses over 6 million gallons per year more than the reduced demand. For this project, our goal is to achieve a minimum of a 30% reduction in indoor water demand. Calculations show by just doing some basic changes in the types of fixtures that are used, there's a 33% reduction in demand, which meets our expectations. Although there was a difference in the annual demand, the pipe sizes for both the baseline and reduced demands were the same. The mains are 14-inch ductile iron pipes, and the laterals are 4-inch ductile iron pipes. To comply with fire code based on the area of the building, there are 6 hydrants located on the site, and each of the hydrants has an 8-inch ductile iron lateral connecting to the water main. Similar to the potable water, the residential and commercial demand were taken into account for the wastewater demand for both the reduced and baseline flows. Based on the number of occupants, their usage of the fixtures, and the given flow rates of those fixtures, the average day demands for both the baseline and the reduced were calculated. The number of occupants in the building indicated that there should be a peaking factor of 4 added to the demands. Using Bentley Flowmaster software, it was determined that the main would need to be the minimum of 8 inches PVC with the 8-inch lateral connecting to the building. Here's a layout of where the potable water lines, wastewater lines, and fire hydrants are located. The potable water mains and the fire hydrants are on the northwest and southeast side of the project, which is the top and bottom in this image. The sanitary sewer is also on the southeast side of the project, and all the pipes are located within the driveway of the project. Finally, a cost comparison was completed, comparing the use of standard fixtures versus water-efficient fixtures to see how economically sustainable it is. Water-efficient fixtures typically have a higher upfront cost of standard fixtures. However, they decrease the water demand in the building, which can lead to a savings on your water bill. The analysis looked at using water-efficient showers, sinks, toilets, and urinals instead of standard ones to see if the decrease in the water bill will pay off the increase in the upfront cost. The 4 main steps in this analysis include determining the total fixture costs based on the average cost of the fixtures and the number of units needed in the building. Next was to calculate the cost of purchased water at this location annually. And finally, we compared the cost and savings and determined the return on investment. The results of the analysis are presented. When comparing just the difference in fixture costs, using water-efficient fixtures cost a little over $26,000 more. But when we compare the water purchasing costs, the water fixtures save around $39,000 annually. This means that a return on investment can be achieved in under 1 year. While the increase in upfront costs is not always the most appealing, we would recommend for the project to use water-efficient fixtures because of the savings over time. And now Rachel is going to talk about our stormwater management on the project.
Thanks, Deirdre. I focus on the stormwater management according to C3 Stormwater Handbook, created by the Santa Clara Valley Urban Runoff Pollution Prevention Program. Sites with more than 10,000 square feet of impervious surface area require stormwater management. Our site is over 137,000 square feet, mandating a stormwater management system. For this scope, we will discuss the chosen management method, proposed placements, and calculations behind sizing, elevations, and cost estimates. The items in red on the right still need to be addressed. We have chosen the bioretention, or bioswale. A bioretention is a low-impact development strategy that uses layers of bioswale, gravel, and plants to treat on-site urban runoff for nitrates, suspended solids, and phosphates. Unfortunately, the water table at our site is very high, so we require a waterproof liner and a connection to a storm drain. Outlined in red are the proposed final placements of a north and west bioretention. The blue arrows show the sheet flow direction of runoff that is requested, and the 2 rectangular brown areas are where earthwork is required in this proposed design. You may notice that the north bioretention is actually outside of the 1200 Campbell lot. According to Jill Bicknell, a licensed PE and author of the C3 Stormwater Handbook, that is all right because the neighboring lot is also owned by Santa Clara. After placing the bioretentions, the next step was to size them. By following Section 4 of Appendix B of the C3, we sized the bioretentions using a combination flow and volume approach for a 2-year storm. The north bioretention's over 3,000 square feet, and the west bioretention's about 570 square feet. Both have a ponding depth of about 6 inches, which is recommended. After sizing the bioretentions, the inlet pipes were next. First, the inlets were placed according to proposed topography, and the lot was broken up into pervious and impervious drainage basins. These drainage basins were then assigned to inlets. After assigning areas to each inlet, the time of concentration is calculated for each inlet using equations from Chapter 15 of Part 630 of the National Engineering Handbook by USDA. Then the time of concentration was used in the USDA hydrograph converter to find the maximum flow rates. Each flow rate was then plugged into Bentley's Flowmaster program to size the pipes at each inlet. A Manning's roughness coefficient of 0.013 for PVC pipes was used, and the flow capacity maximum was set to 60%. Using the minimum required slope of 1%, these are the pipe diameters at each inlet. The smallest is at inlet J on the southwest corner, and the largest are at inlets B, C, and G on the north side. Sizing the underdrain pipes was next. The maximum flow rate of each underdrain was calculated by multiplying the surface area of the bioretention by the infiltration rate of 5 inches per hour per the C3. Flowmaster was used again to size the pipes, but with a minimum required slope of 0.5%. The last pipes to size were the outflow pipes coming from the overflow structures. We followed the bioretention sizing worksheet in the C3 again, but used a 10-year storm with the existing bioretention surface areas. The excess ponding depth beyond 6 inches was used to calculate overflow volume. Then the maximum flow rate was calculated by dividing the overflow volume by the longest time of concentration plus the storm duration used in the 2-year storm. This maximum flow rate was plugged into Flowmaster again to size each bioretention's outflow pipe. Here is the proposed final layout, including pipe sizes, lengths, slopes, and elevations. As you can see, we are using pop-up emitters to ensure that runoff is directed to the bioretention with no backflow of ponding water. Pop-up emitters are already being used at existing bioretentions on campus. Finally, we conducted a cost estimate for constructing and maintaining both bioretentions. After designing cross-sections per the C3 construction drawings, material estimates were calculated and plugged into RS means. We calculated the 10-year maintenance cost of 12%, which is an industry average, using 7% annual inflation. The total cost, including overhead and profit, is just above $90,000, and the total cost of maintenance is just over $106,000. Let's put that cost into perspective. Green roofs are another form of LID that are commonly used for on-site stormwater management. Using EPA rates of cost per square footage for a green roof, here are cost comparisons between our bioretention and a green roof. Even on the lowest end of its cost scale, the green roof is about 8 times more expensive, which is why we are using a bioretention. Continuing this vein of cost estimates, Aya will discuss the construction management of this project.
Thank you, Rachel. Now I'd like to discuss how all these scopes come together and how we envision this project to be constructed. The construction management of this project contains 5 main categories: the project management, the building information management, the project cost estimate, a full project schedule, and finally 4D modeling. Design items listed in red are the ones that are omitted within our construction scope. This project will take a design-build approach. Based on research performed by the Design-Build Institute of America, Design-Build allows our team to effectively overlap design and construction, expedite the start and end times of construction, as well as streamline the communication and risk under a single contract. This effectively leads to less risk for the owner, SCU, and comparatively an easier project to manage in comparison to other traditional methods. To ensure that this project remains on track for design-build delivery, the following programs will be utilized throughout the design and construction phase. During pre-construction, Microsoft Project allows all stakeholders to view expected project progress, provides 3 weeks look-aheads for AOC meetings, and assists in the coordination of MEP subs. Autodesk Revit offers the ability to visualize the entire project on a macro level. Using BIM, it also offers a unique tool to reduce scope clashes among competing trades, often require precise specifications for install and maintenance. Synco Pro is a powerful virtual construction software that combines the BIM model with the project schedule and offers real-time phasing of construction activities and value engineering. It presents a piece of information for stakeholders throughout the entire project, as they'll be able to plan ahead for the variety of different scenarios before and during construction. And as the project breaks ground, Procore's comprehensive file collaboration system will allow for an increased productivity between stakeholders, and Bluebeam will expedite the RFI and submittal review process. BIM modeling allows our design team to effectively expedite construction, as well as limit the amount of clashes between scope. In the model we have here, we see the superstructure, exterior walls, interior walls, foundation, topography, and other amenities that will be included within the full report. Over 41,000 elements were modeled in this project file, which each item containing editable parameters, often called parametric modeling. Parametric modeling through Revit's comprehensive family system allows for great control over scope changes and class identification. The elements in this project were categorized using CSI's master format divisions, which covers metals, concrete, openings, and HVAC, among other things. With these divisions, 3 different types of estimates took place: a detailed unit cost estimate, which estimates concrete and steel, an assembly cost, which includes stairs, assemblies, and square foot estimate, which covers items out of scope. Material and labor prices were also multiplied by 1.2.9 to account for San Jose's inflated costs. With the design build approach, our team decided to pursue a guaranteed maximum price pay structure, as we are confident that the project will be delivered on time and under budget, with the confidence sprouting from the use of BIM and 4D modeling. A design fee of 10% will be added to account for the initial modeling and increase LOD of our BIM models as they progress. Our overhead and profits sit at a modest 10% and 5%, respectively, with any savings split between the owner and the GC, with a 70% going to the owner and 30% going to the GC. This brings our total cost for the project over a little over $96 million. A breakdown of big ticket scope items such as metal, HVAC, and furnishing are listed in the graphic shown. The project schedule includes over 200 items. The overall project scope is presented here, as well as the critical path of the project. In order to meet our design build goal, the critical path is important to identify, as missteps in the schedule can lead to failure of completion of our project. Construction is projected to start on April 21st, 2021, with sequencing starting with site work, moving to foundation, then superstructure, MEP, exterior wall, and then finally rounding off exterior walls and finishes. And finally, to tie both the BIM model and the project schedule together, the use of Synchro Pro, a 4D modeling software, offers a time-sensitive representation of the model as construction takes place. Animation of the construction of all major scopes associated with the project has been created with this video. As you can see, the steel framing and the concrete columns and walls have been constructed, and each level follows each other. Along with this project schedule that I created, you can see the exterior walls lagging behind the floor construction. As you know, to be most productive, that's the approach that we took for this project. Synchro Pro offers such a valuable use case for the project owners, including all the subs, main contractors, and especially anyone who wants a visual representation of how the project is going. And now I pass it off to Deirdre for our closing statements.
Thanks, Kyle. We will now begin to conclude our presentation. But before we do, here's a recap of everything we've presented this far. Spencer completed the structural design, which included the building skeleton, the selection of materials, and the gravity and lateral systems. I presented the potable water and wastewater management civil design and completed a cost comparison of using more sustainable features. Rachel presented on the bioretention, which was a stormwater management system of choice, and completed a cost analysis for the stormwater management. And I presented our project delivery, the implementation of BIM in the design, a project estimate and schedule, and how we incorporated Synchro on the project.
On behalf of the entire design team, we would like to thank everyone who played a big role in allowing us to learn and grow as civil engineers. We appreciated all of your help, patience, and encouragement throughout this entire project.
Thank you very much for listening to our presentation. Now we'll open up for questions.